availability in another way. And there are several options that can be used. And in this subject, we will consider a few of these options, the most used. And given that rainfall data are more readily available, this is one of the options. Basically, what is the input of water to the process that generates the river flow is rainfall or snowfall, it's precipitation. So basically you have a natural process that, starting from precipitation and taking into account several other variables, ends up by generating the river flows. It's a natural process which we don't know. We know it in principle, it's part of the water cycle, but we don't know the details. But still, even if we didn't know the process perfectly, we can try to build a mathematical model. And the reason why the measurement of rainfall are much more readily available is that, as I mentioned to you before, it's very easy to measure rainfall. And therefore, in a given region, it's very easy that you find rainfall data. It's unlikely, as I said, that you find river flow data. So the idea is rainfall runoff model. Look, there have been some studies, that proved what is the precision that you can reach with this kind of technique. What is the level of uncertainty? And some of these studies concluded that it's preferable, it gives less uncertainty to put in place a river gauging station and use very short record of data. Like, let's suppose that you have to design this water withdrawal and you have a couple of years' time, because sometimes, of course, you are contacted in advance and then you need time to prepare the project, etc. One possible solution, if you don't know anything about the river flow, is to put in place a river gauging station, a water flow measuring station, as soon as possible, and then, once that you need to design your work, use the data that meanwhile became available. And of course, this solution has the disadvantage that you don't have long records, because it's unlikely that more than a couple of years are given to you to elaborate, to design a water withdrawal and hydropower plant. So to use observations that were collected during 2 years only, it means getting uncertain estimates. But still, these studies that I mentioned to you before proved that with 2 years of data measurements only, you reach a better precision, you reach a reduced uncertainty with respect to using mathematical models. This is not a general result. You can't take it literally. But I just want to give you an idea, because in some cases, maybe that you look for observation and you find some of them. You find like 3 years of data, so you may say, yeah, it's not enough, and I need a mathematical model. I came to the conclusion that if you have 3 years of data, it's a very lucky situation. It's probably not worth building a mathematical model if you have 2 or 3 years of data. Still, the mathematical models may be useful, because if you really don't have data, they are useful, and also they could be useful to compare the results. So in many cases, I had observations. The observations were deemed to be uncertain, and I built a mathematical model for comparison. Just in order also to convince people, because when you discuss with people, people say, okay, the observation will be uncertain, and therefore if you are able to say, okay, but I also built a model, to provide a comparison is always a good thing. So rainfall runoff models indeed are an interesting option for us. And in water resources management, they are usually frequently applied. And rainfall runoff modeling is a typical topic of hydrology. It's one of the major topics of hydrology. So now let me try to go into the details. This is just an introductory slide. I think I don't have anything to say about that. And this is a picture of hydrological cycle, and we already spoke of it, so nothing to say. And this serves to me just to get into the context. Let me move forward. Again, hydrological. Now, this is a sketch of a model, and of course, this is a model that is representing the many processes that are involved in rainfall runoff modeling. And I don't want to spend much time on this picture. I just want, because we will have time to discuss later on this. And the scope of this picture is to make you aware that the rainfall runoff process is a very complicated one. Because even if you have rainfall measured, then you have to decipher a lot of physical processes. And in some cases, also chemical processes that lead to the formation of the river flow. And among these processes, there are those governing the groundwater flow, for which, the control volume is not well defined and not observable. These processes are not observable. So it's really complicated. But of course, like any mathematical model, we can simplify it. And we will see how to simplify it. Okay, let me introduce getting into the mathematical context by recalling some of the principles that I already introduced to you. Models, mathematical models, are given by systems of mathematical equations. And the number of equations, as you know, should be equal to the number of unknowns. The unknowns are the output variable in which you are interested in, plus any state variable that you may need to introduce. So you have, among the unknowns, you have the output and the state variables. What are the state variables? Are variables that quantify the state of the system. So basically, in a system, you have the system that you want to model. Let's say that is depicted by this rectangle. You have input variables you have output variables and then you have state variables. What are the state variables? They are variables that are needed to establish a relationship between the output and the input. And let me give you a very simple example. If you want to describe the river flow and your input is rainfall, it's very easy to understand that the response, the output, the response of the system to rainfall, the response of the system is the output, depends on the water that is stored in the catchment when you get the rainfall. If you get rainfall on a dry catchment, you get a reduced river flow. If you get rainfall on a wet catchment, then you get maybe a flood, even if the rainfall doesn't change. The same rainfall could end up in a flood or could end up in a river flow that is close to zero, depending on the water that is stored in the catchment. You may also call it soil moisture. Then, the water storage in the catchment of the soil moisture, they are an example of state variables. You need these state variables to connect the input to the output, even if you are not really interested in knowing what is the water storage or the soil moisture. You are not interested in knowing that. You are interested in knowing the output. But you need the state variables, and given that they are unknowns, you have to compute them among your unknowns. Sometimes it's not so rigorous, the distinction between output variables and state variables. One guy could say, I am interested in soil moisture because I want to know if I can cultivate some type of crops. So I also want the soil moisture simulated. So the distinction between, the difference, distinguishing between state variables and output variables, it's a distinction that is not rigorous, and we are not really interested in distinguishing, because our purpose is just getting to the output. We really don't care if the water storage in the catchment is a state variable or someone calls it output variable. But it's important that you keep into account that you may need additional variables besides additional unknowns besides the output to describe your system. This is the moral of the story. To describe the output, depending on the input, you may need to introduce additional unknowns. So you need a set of mathematical equations to describe these unknowns. And the question is, what kind of principle can I use to derive these mathematical equations? And then the reasoning comes that I anticipated to you, that in fluid mechanics, hydrology basically is a description of the movement of a fluid, which is water. And in fluid mechanics, we know that conservation of mass and conservation of energy always apply, as well as the Newton laws that you see described here. So your principle, which translates in equations for building an hydrological model, are first of all conservation of mass of water and conservation of energy and momentum also. And then let's also remember the Newton laws, which are always satisfied in fluid mechanics. So every object in a state of uniform motion keeps this state unless an external force is applied. And then you have the second law, F equal m times a. Force is equal to the product between mass and acceleration, which we know very well, because in your ground you for sure had some physics. And then for every action there is an equal and opposite reaction. Usually in hydrology we don't use the Newton laws, but we use conservation of mass, energy and momentum. So basically these are the basis for computing the water balance and rainfall and off modeling. Now, hydrology has a problem. When you apply mass balance and conservation of energy or momentum in Italian is quantitative moto, but I think you already know this. And when you apply this relationship, you have the problem that hydrological processes are highly heterogeneous, meaning they are characterized by a very significant spatial variability. And also, they are highly varying in time. So what is the consequence? Because there is an important consequence that if you impose the conservation of mass or the conservation of energy, this relationship need to refer to an infinitesimal time and an infinitesimal element of space. Because, you know, if, for instance, let's think about the conservation of mass. conservation of mass, the continuity equation contains the velocity of water, as we will see. But the velocity of water in hydrology is highly varying in space. Or if you think that rainfall is highly varying in space, so your input data to the system are highly varying in space. Which means that if you want to identify the area where your measured input is valid, is very, very small. So if you have a rain gauge measuring rainfall here, you can't apply this rainfall to the whole table, because there you could have zero rainfall. And here you could have a very severe rainfall. So you can't apply this input data to the whole extension of the table. You need to apply just in a very, very small region of space. And the same for time. If you measure rainfall in 1 second, like now, at this time, you can't assume that this rainfall is constant for 1 hour. You need to refer to an infinitesimal time. So basically, this balance equation, they are expressed in the form of differential equation, which refer to infinitesimal element of space. Infinitesimal is correct in English? Yeah, okay, thank you. So basically, this is a bit of a problem because, you know, the river is very huge. And also, if you think to the area, if you think at the area that is feeding water to the river, which is a catchment, it's huge. So, this means that our rainfall and off model cannot apply to a large spatial scale. It can only be applied to a very small spatial scale through differential equations, which is a complication. Okay, before I move forward, let me provide a couple of definitions. And the first definition, which is extremely important, and I may ask you to examine these definitions, so please try to make sure that they are clear for you. And if they are not, just let me know. And I'm not sure I have a slide later on providing these definitions, but I will dedicate some time to them. So first definition, and let me turn. I'm not sure if, let's see. No, yeah, this was a big mistake. Before I can get back to the, I wanted to turn the light on, but I turned off the projector, so this is a big mistake. Let me just turn it on again, with the hope that it doesn't need to sleep. No. Okay, should become working again in a short time. Okay, let me provide the first definition. Catchment. Okay, and this is also called, I think, catchment is American English. In the British English, it should be watershed. And I use them as synonyms. And also another synonym could be river basin. So, what is a catchment? Or river basin? Or watershed? First of all, we need to refer to a river cross section. And let me make a sketch. Let's suppose that you have a river, and at a certain point you get a location along the river. And this location is identified by a cross section. I will need another definition for cross section, which I will provide to you later, but let me anticipate for now that it's a given location along river reach. Like a bridge. If you go over a bridge, you are over a river cross section, because the bridge crosses the river. And with reference to a cross section, the catchment is the geographical area such that all and only the rainfall over that area contributes to the river flow in the given cross section. I'm repeating. For a given river section or river cross section, I think it's a river cross section, the catchment is the geographical area such that all and only the rainfall that occurs there contributes to the river flow in the given cross section. Basically, the catchment is the geographical surface that collects the water that goes into the river. And pay attention when I said all the rainfall that flows there contributes to the river flow, but only that. Which means that you can have an area here where if you get some rainfall, it flows there, because then this will be part of the catchment. So once that you identify the catchment, you know that all the rainfalls that flows there contributes to the river flow. All means that you don't have rainfall flowing up somewhere else, and only the rainfall that flows there contributes to the river flow. So identifying the catchment is very useful, because you know once that you have an estimate of the rainfall of the catchment, you have the input water to your rainfall and outflow. All and only the rainfall that occurs over the catchment contributes to the river flow. Okay, that is a catchment. And then I anticipated that it's better if I provide a definition of river cross section. And let's suppose that you go along a river, and let me magnify, let me see a river from above. So you have a river here with the water flowing in this direction. And let's suppose that in a given, you take a given fluid particles, like this one, and you estimate for this fluid particle, the velocity vector. And let's suppose that is this one. Okay, now let's cut the river, and this is seen from above, as I said. Let's cut the river with a plane that is perpendicular to this velocity vector. And let's look now in section to the picture that you obtained, which is something like that. Where the velocity vector, this is our, for instance, fluid particle, and the velocity vector, if you look from downstream, is exiting from perpendicularly to the blackboard, because I cut the river with a plane that is perpendicular to the velocity vector, and then if I look from downstream, I get this picture where that is obtained by cutting the river flow with a plane that is perpendicular to the velocity vector in this fluid particle. And therefore, if I locate the fluid particle here, then I see the velocity vector that comes out from the blackboard and is perpendicular. Okay, this is the cross-river section. And you may say, yes, but if I take another fluid particle here, let's say here, and here, I may find another velocity vector, and therefore, this particle, which belongs to this river cross-section, could have a velocity vector that is not perpendicular to it. Okay, this would be a good question, and I would reply by saying, in hydrology, we assume that the flow in the river is 1D, is monodimensional, which means that in the river cross-section, you have the velocity vector that is constant. This is an approximation which is largely used in hydrology. So basically, this is the definition of a river cross-section. Let's say that at any location around the river, you have only one velocity vector. If you cut the river with a plane that is perpendicular to the velocity vector, you get this picture of the cutting, which identifies your cross-river section. And in the cross-river section, you have constant velocity vectors for all the fluid particles that belong to it. Third definition, river flow. River flow is always referred to a cross-river section, and it's the volume of water per unit time that passes through the cross-river section. Again, the river flow refers to a cross-river section and is defined as the volume of water per unit time that passes through. Yes, please.
How much about
Sorry, say again.
like by assuming the constant velocity of the river, how much wrong? How much does the end result deviate from the real river flow? Is it a big assumption by the?
Okay, you mean how reliable the assumption is?
Yeah. Exactly.
Okay. First of all, if you consider a river in general, you have, of course, you don't have constant velocity in a river cross-section, and it's not constant because we know that close to the river bed, you have a velocity of the fluid that is zero. Strictly speaking, if you look at the river bed, the velocity of the fluid is zero. And therefore it means that getting closer to the river bed, you have a reduction of the velocity. And also, if you look at the vertical direction, and if you look at a river, and this is a longitudinal section, so you have the water flow in this direction, and this is the free surface of the river, you get a diagram of the velocity that is about like this. So you have the maximum velocity close to the surface, but basically the estimate is about, if this is h, the total river depth is h, you get the maximum velocity at about 0.7 h. But, so if you want to be detailed, you should of course say that the velocity is not constant, and the variability depends on the behavior of the river. If you have a river like this, the variability is not very significant. If you have a river with floodplains, the variability is important. A river with floodplains means that you look at the cross-river section and it's something like that. And you get your cross-river section that is, you know, the geometry is very complicated. And of course you get a much higher velocity in the middle of the river than in the floodplains. So basically this is an assumption that we know it's valid under certain conditions, and we are much interested in hydraulics to describe the conditions under which the assumption is reliable. In hydrology, basically, you are not interested in a so detailed description. And this is the reason why we assume that the flow is 1D and we don't care about it. And the reason why we don't care about it is that in hydrology there is an uncertainty that is much significant than in hydraulics, because if you look, for instance, at rainfall, you have a measurement error that is about 20%. So it's, you really don't care by an assumption of 1D flow. And so river flow, as I said, it's an important definition, and given that it's a volume per unit time, if you look at the units, they are a length squared divided by time. And very often we use in the international system cubic meters per second, and but very often it's also used liters per second, and especially in some technical fields of application, especially when the flow is very small, not typically for rivers, but for instance for pumps, they use liter per second. And it's necessary that you know that 1 cubic meter per second is equal to 1,000 liters per second. So don't forget this. It's extremely important to know. I may ask at the exam, how much is 10 cubic meters per second? And you have to say, in terms of liters per second, you have to say 10,000. Okay, so 1 cubic meter is 1,000 liters. This is the basic thing that you have to remember. Okay, so we have defined the catchment, the cross-section and the river flow. Final definition for today: concentration time, or time of concentration of a catchment. In Italian it's called tempo di correlazione. Time of concentration. What is a time of concentration? Okay, let's suppose that you have rain over this catchment, and let's take the point in the catchment which is located much farther from the closure. The closure is the river cross-section that I use to define the catchment. It is also called the closure. So let's take the point that is located much farther from the closure. And when I say much farther, I mean the hydraulic path. So the point that is much farther, it would be this one. If the river network is displaced in such a way that a drop that rains here has to go like until here, and then here, and then here, and then here, and then here. So I'm not speaking of distance, net distance, geographical distance, hydraulic distance, distance measured along the river network. So let me refer to the point, to the drop that is located much farther from the closure. Then the time of concentration is defined as the time taken by that drop to reach the closure. And the you want to say it in only one sentence, is the time of concentration is the time taken to reach the closure by the drop of rain that is located much farther from the closure itself in hydraulic, according to the hydraulic pathway. So it's the time required to reach the closure section by the drop that is located much farther from the closure itself in terms of hydraulic pathway. And this definition is clearly imprecise, because you may ask me, what about infiltration? So if the drop infiltrates and then stays in the underground for several years before going back to the surface, these several years are part of the time of concentration, and this is not defined. The literature doesn't tell you. It is implicit that we refer to a surface travel, a surface trip. But indeed, it's the time of concentration, let me say, in a paradoxical way, that it doesn't exist. It doesn't exist, it's not measurable. And it's a proxy time to define what? It's a proxy time to define the time after the end of a rainfall, after which you don't see any more significant effect of that rainfall on the river flow. So let's suppose that now stops raining, and you see the sun in the sky, but you still see the river flow that is higher than usual. There might be still a flood. And then after a while, of course, it doesn't rain anymore, and you see the river flow decreasing. Until after a certain time, you see that the river flow comes back to a normal situation. This certain time required to the catchment to